In this video lesson, we are going to learn about comparing two population proportions. So the idea here is that we start out with a general population proportion, and as we have learned from our previous understanding, that population proportion is always regarded as a lowercase letter p. And once we have defined a population proportion, we would then separate our study about this population proportion into two separate different populations. And so allow me now to bring up an actual problem as a scenario here. And through this problem, we are going to learn the idea. And I will be highlighting a few important concepts before we actually get into the actual work of comparing the two population proportions here. So let's now look over at my scenario that's being brought up on the computer screen here. So what we're looking at right now is nothing but just the description of two separate samples. But let's spend some time reading the two samples here, the description of the two samples here a little more closely, and then we will recognize what's going on here. So in a sample of 450 male drivers, we found that 170 of them favor driving a manual transmission. And that's the end of the description for our first sample. So obviously it says this is a sample that's being as large as 450 male drivers. So this sample is clearly selected from the population of male drivers, because there are a lot of male drivers in the world. And then at the end of that description, we move on to the other description of the other sample. In a sample of 450 female drivers, we found 100 of them favor driving a manual transmission. And so how I see it about the two samples here is that at least there's one common thing we want to look for in both of these two samples. And the common thing I'm talking about now is that among those samples, we're looking for those drivers who favor driving a manual transmission. Favor driving a manual transmission. And of course, manual transmission is the formal name for driving a stick shift car. And so right out from that, now back on my writing board here, then we can define. So generally throughout the population of drivers, not specifically male, not specifically female, just generally throughout the entire population of drivers, we can define that population proportion. That's called, so now lowercase letter p is the proportion of drivers who favor driving and allow me to use a shorthand writing about an MT. That's short for a manual transmission. And so clearly speaking, P now is the proportion, generally the proportion of drivers who favor driving an MT or a manual transmission. So that's the scenario that I would like to bring up. And as of right now, looking at this proportion, it's just some general proportion in the entire population of drivers. Again, back into the wording description of our two samples here, then clearly we have had one sample as highlighted in yellow here, being selected from the male drivers. And for now it's a little ahead of time, but in this sample we found 170 of them. So if we put 170 out of 450, we have a proportion. But this proportion, 170 out of 450 male drivers here, is only a sample proportion of those drivers who favor driving a manual transmission, taken out from within the male drivers population. And the same as the other proportion. If we put 100 out of 450, we have a sample proportion of those drivers who favor driving a manual transmission. But taken only from the female drivers population. And so my point now I would like to make is that the same proportion now, the same general proportion of drivers who favor driving a manual transmission, we now separate it into two separate populations. So we're gonna have one separate population as the male drivers, and there's another population being the female drivers. And so now that general proportion can be looked for in the male drivers and also be studied in the female drivers as well. And so now in that matter, we need to find a way to keep our work organized, because we will be studying the same proportion here but in two separate, and it will always be like that, one population parameter, but we are studying it in two different separate populations. And we would like to find out how far different they are, how far different the parameter is in the two separate populations here. And so to make the later work convenient for us and easy to handle, we come up with the idea of giving a numerical label for each of these populations. And so now I am going to call the male drivers population 1 and the female drivers population 2. So I have to now be clear that giving a numerical label is only to keep the later work, organized and easier to handle for us. But giving a numerical label like this does not mean any way at all that male drivers population is more favored than the female drivers population, because right at the beginning, as I was setting up the two numerical labels here, this male drivers population could have also been population number 2, and the same for the female drivers. It could have been labeled the other way as well. But the reason I chose this initial choice here, population label 1 for male drivers and population label 2 for female drivers, simply because right now, as the way how it looked in my current data, then the male drivers was described first. So I just simply take on with that order and define the two numerical labels in this way, in that order. But so now, upon deciding the numerical label for our two populations, then that brings a tremendous usefulness for us. So from this point on, anytime we need to reference back to any one of these two populations, we don't have to keep referring to these as male drivers or female drivers populations. But from now on, any later time when we're doing our work, we can just simply refer back to the male drivers population as population 1 for short. That's the first impact. And the female drivers, instead of calling with a long name like this, later on at any step in our work where we need to refer back to this population, the female drivers population, we have a better name, a more convenient name, the population 2. And so now, as I said earlier, this same general population proportion of drivers who favor driving a manual transmission, now if we specifically study that population proportion within this population 1, then here's the next usefulness. The same population proportion there, lowercase letter p. But now if we're looking for that or studying that in population 1, within population 1, then at any point in our work, we would like to refer to this population as P1. And so I use a subscript 1 right here to indicate that this is a population parameter, this is a population proportion value. But the subscript 1 explains that this value is specifically studied or specifically belong to population 1. And so similarly, this same population proportion of drivers who favor driving a manual transmission. But now if we're looking for that, if we're studying that within population 2, then it's a lowercase letter p for population proportion. But now I would assign a subscript 2 for that. And so the subscript, at this point now, anyone viewing the video will notice I use a subscript to be consistent with the numerical label for that particular population where our value came out from. And so as a usefulness about doing this, anytime later on in our work that I need to refer back to the female drivers population, and specifically the proportion of female drivers who favor driving a manual transmission, I can just quickly refer to that as P2, because it's a P generally is the proportion of drivers who favor driving a manual transmission, but P2 is simply indicating that that same proportion is being specifically attached to female drivers or population 2. All right, and so now we are ready to dive into further details as we keep breaking down our description of the 2 samples here on the computer screen. So now let's specifically look at the sample from the male drivers population. So now this is a sample that's clearly from population 1 in our new language, in our new term where we call the male drivers population here as population 1. So this sample comes out from population 1. And so here's the thing, this sample size, this 450 is the size of how big our sample is from that population 1. And so in that way, on my board, I have a sample size that I selected. So it's a sample, and the sample size I selected from population 1 here being as large as 450. And so now in the new convention about the numerical labeling that we have just now decided, then this sample size here is the sample size that I used in population 1. And so I call that now N1. And so I have to be clear that this is the sample size where, once it's decided on specifically population 1, then any other samples being selected from population 1 must agree with this specific given sample size, being 450. And so, once again, the subscript 1, which is written in red ink right here, is only to indicate that the sample size we use here is a sample size specifically decided for population 1. So anything that comes out from population 1 has subscript 1. And so let's now look further into our description of the 2 samples. So still in the same sample that is from population 1. So now if I spoke about this a little earlier, so now let's look into that a little further. So now in this sample of 450 male drivers, or in this sample of 450 the people from population 1, we found 170 of them who favor driving a manual transmission. So right here with the 2 numbers that I highlighted, this is the successive count that we found those in this sample that favor driving a manual transmission. But now on my board, and the work now is starting to become familiar. If we simply set up that count, that successive count, 170 over 450, our sample size, and of course these numbers are all from population 1. So 170 out of 450 is the proportion. It's the proportion of drivers who favor driving a manual transmission. But then this proportion is only a sample proportion. So in our understanding up to this point, we must refer to this proportion as a p hat value, not the actual lowercase p. So it is a lowercase p, but with the hat, simply indicating that it's only valid. This count is only true in this sample being described in our data. And then now further, under this convention about the numerical labeling we gave for the 2 populations, then I would refer to this p hat as now p hat 1. And so with a quick calculation, my value for p hat 1 here is, and usually for proportion, any proportion values, including the sample proportion values like this, I am going to round to 4 decimal places. But I leave that for viewers and my students to watch for any rounding requirements for proportions and sample proportions in different various problems. So here 170 out of 450 is 0.3778. So this is our sample proportion, and since it came out that we selected from population 1, and so it gets that subscript 1. So p hat 1 is our current value right here. And so now that's all of the description for our sample that came out from population 1. Let's now move on to the other sample. So let's now turn our focus to the computer screen here. And so now, on the other hand, in a sample of 450 female drivers, so this highlighted information here, it's indicating that we selected 400 female drivers from population 2. Or in other words, now this is a sample that is from population 2. And specifically, 450 here is how big that sample we selected from population 2 is. And so now, very similar arguments. Now I have a sample size for any sample selected from population 2. And that sample size there equals 450. And now in the same argument that I've made earlier, this sample size is the sample size that we decide for all samples selected from population 2. So this sample size here is being referred to as N2. And so this sample size gets a subscript 2 simply because this is the value that we specifically isolate that within population 2. And now again, back into the reading description of our samples here. So in this sample from population 2, now I can officially say that, then we found 100 of them. So this is again the successive count for those drivers who favor driving a manual transmission. But this successive count was found in the sample that came out from population 2. And so now back on my board, it's a proportion. So if we put 100 out of the sample size 450, it happens to be the same sample size from population 1, but it's intended to be a different sample size, decided differently, and I will get to that a little later. But so now in this current sample from population 2, 450 female drivers, we found a successive count of those who favor driving a manual transmission to be only 100. So 100 over 450 as a proportion here, we refer to this as a sample proportion because it's a proportion, but it's only valid, it's only true within this sample that we found from population 2. And so further, again, this sample was selected from population 2. So this p hat must get that subscript 2 to indicate where it came out from. And so a quick calculation again gives me 0.2222. And again, I stay in my own choice for rounding to 4 decimal places for all proportion and sample proportion values throughout all of my video lectures. But I leave that for viewers and students to watch for your own rounding requirements in each problem that you're doing, that you're working with. So now I call this value in decimal 0.222 the sample proportion, but more specifically, this sample proportion was selected from population 2. And so now I once again need to recall another idea that any viewers who have arrived at this video lecture must be very familiar with. The idea is as following. Let's say now we focus ourselves to one specific population. So let's look at the population 1 first. So now we know that we're in population 1. And Now looking at the sample, once we can have one sample or a sample, then we can have another one. And so this could be our first sample, that is from population 1. And so the subscript here is indicating that it's from our population 1. But now, as we have been well familiar with, then anytime we can pick out a first sample, then we can pick another sample, provided that it's from the same population. And so in that way, maybe right now in our current sample, p hat subscript 1, it's our first sample. We found that to be 0.3778. Somebody else may have found a different sample, but from the same population, and that's why it gets subscript 1. So now, again, to be clear, subscripts are used to indicate where the values or the samples came out from. And so we had another p hat value. It could be the same value or a different value with this first p hat, but my point now is that we can end up with a lot of p hat values, a lot of sample proportion values. So to name them, to name who's the first one, we use a superscript. So p hat 1 with superscript 1, that's indicating, and maybe this is really our first sample. So I call that this is p hat 1 with first sample. And so in that way, if for any reason another sample from population 1 again, then we call this p hat 1 but with a superscript 2, indicating that this is second sample. And so, but obviously I did not have any other sample other than this, only one I have, so I'm going to have to leave it blank or as dots. Then we can have a p hat from population 1 but third sample as a third sample proportion. And since so we can possibly have any of these. It's just right now in our particular data that I showed on a computer screen, we didn't have any other sample values other than this particular one that we have. So again, I'm going to have to leave p hat 1 third sample empty. And so expectedly, in this way, we can find infinitely many other sample proportions from population 1. And another idea I would like to remind anyone now is that all of these samples, as long as they come out from the same population, and as I said earlier, that now we're currently restricting our attention to population 1, for example, then all of these samples, and regardless of how many samples we are attempting to reach, all of these samples must agree to be of sample size n1, being 450. So apparently p hat 1 first sample was out of 450, but if we would obtain a p hat 1 second sample or p hat 1 third sample or so on and so on, any of these other sample proportion values must agree with the same sample size that we have already decided from the beginning. And this is the one that I call N1 right here. So N1 is the sample size that's being decided for all samples that we picked from population 1. And so the same way, now if we turn our attention to the other population, namely population 2 now, then the sample we currently have, I can call that the first sample. So subscript 2 is indicating that it's from population 2, clearly, but we can regard to that as our first sample. And so the value for that we have right now, 0.2222. So this is a sample proportion value, and I refer to that as p hat 2, but first sample. And then again, just like how I have selected, how I could find infinitely many sample proportions back in population 1, I can do the same here too. Once I can find a sample proportion from population 2, I can find another one. So I'm going to call that p hat 2 with second sample. So the superscript again is to indicate the order of the sample that I created, in case where I have multiple samples from the same population. And apparently I did not have a value for this second sample from population 2, so I can just leave it as a blank. But very possibly we can have a third sample from population 2. So pH2, third sample. And again, I didn't have a value, so I'll just leave it blank. But now similar arguments that I've made back in population 1 right here. Then all of these samples, and including all of those that can possibly come out, they must all agree to be on the same sample size that we have decided for population 2. So now that's the meaning of what N1 and N2 is. So N2 here is also decided to be 450. And so in that way, how I explain now, then the sample size N1 and N2 here, the truth is they do not need to equal, because sample size N1 only means that it's the sample size we decide for all samples being selected out from population 1. And sample size N2, the subscript 2, only means that the sample size here is the sample size that's decided for all samples selected from population 2. But as a matter of fact, these two sample sizes, they are being decided on two separate populations. So there could be reasons out there where statisticians, scientists, or researchers stick with sample sizes on two separate populations being different. So in other words, now my point again is that these two, N1 and N2, the not equal sign here only means they do not need to equal, or need not equal, that's for short. N1 and N2 need not equal. And again, back to what I was halfway saying, there can be many different reasons that scientists or researchers or statisticians choose the sample sizes N1 and N2 to be different. Here we only take we only need to take that fundamental fact that these two are not restricted to be equal. They can just be two different values, even though the two sample sizes here happen to be decided equal. And so now, to advance further, I need to come up with another definition. So now apparently that we have investigated what it means by being a P1 and a P2. So now I specifically define, so it's a definition here. I define the following quantity, dP, to be the difference P1 minus P2. And as a matter of fact, I should have labeled these subscripts with red ink. And so dP for now is simply just a definition. So D here looks like it's intended for difference. So dP is defined as a difference between P1 and P2. So it's a definition to pay attention to. But now after I put this definition in a box, I want to emphasize that the reason I changed the ink color of the two subscripts here from originally black to now red ink, because I want to emphasize the fact that dP, the difference in the two population proportions here, is permanently defined as the population proportion from population 1 subtract the population proportion from population 2, regardless of who's playing in the role of P1 and who's playing in the role of P2. We will always want to define, we will always stick with this definition where dP, the difference in P, the difference in population proportion, is P1 minus P2. Now, so the reason for what I've just said now is that, think about it, right from the beginning, I could have defined this population to get numerical label 2, and this population here could have gotten numerical label 1. So this P right here could have been P1, and this other P value could have been P2. And so in that way, if I decided the numerical labeling convention from the beginning the other way around, then all of these subscripts gets turned around the other way. But the definition will stay the same. I always want dP equals P1 minus P2. So that's the first thing I would like to clarify about that. And we will understand the greater impact of staying with this particular order of the definition. And order, I mean the number 1, the value that came out from population 1 always stays in front of the minus sign, and the value that comes out from population 2 will always stays after the minus sign. So for now we keep that as a definition, and the convention here is we always want to stay in that order where population value from population 1, whoever that is in that row, minus population value from population 2. And so now, since we start getting into talking about the difference between value from population 1 and that similar value from population 2, then let's apply that to our samples from the two populations here. So let me do this. I am going to draw a line that connects, a short line that connects my first sample from pH1 right here with second sample from pH2, because now pH1 and pH2 are rather two different families of sample proportions, or two different sampling distributions of sample proportions. So now this line right here connecting pH1 first sample with pH2 second sample is to indicate that I can create a difference. I can create a difference that, and again, the convention here is value from population 1 minus the value from population 2. So I can create a difference pH1 first sample minus pH2 second sample. So that's just one possible difference between two samples from two separate populations. Or aside from that, I can subtract directly the two samples that I'm currently having. So again, this line, this short double arrow line right here, connecting between pH first sample and pH1 first sample and pH2 first sample, is to indicate that these two can create another difference. And again, that difference there represented by this connecting line is pH1 first sample minus pH2 first sample. So it's a different value. It may give a value equal to what we have had earlier, pH1 first sample subtracting pH2 second sample. They could be the same, they could be different values, but in the end these are all differences between a sample from population 1 and a sample from population 2. And again, we stay permanently in that convention, that value from population 1 minus that similar value from population 2. And so like that again, I can connect these two samples like that to create a difference in my two samples. Or I can create a line like this connecting these two samples. And so in this way, now all of a sudden we realize we can have infinitely many values where each one of those values is a difference between a sample from population 1 and a sample from population 2. So now after that explanation, here we come to another definition, getting ourselves ready for getting into the real problem in comparing two population proportions. So the next definition I'm about to point out now is that right out from what I have described here in the situation, then we can always pick a sample proportion from population 1 minus the similar sample value from population 2. And now I call this difference, it's a dp hats. So these are all lowercase, and the hats is indicating that these are all intended for sample values. But so now upon defining this difference right here, the difference between a p hat 1 and a p hat 2, and as I just said, a p hat 1 and a p hat 2, it is now important that I must clearly define what p hat 1 is. So p hat 1 in this definition means or is a sample proportion from, importantly, population 1. But focus, pay attention to my word over here. I'm saying a sample or any sample. So p hat 1 here just generally represent any sample proportion from population 1. Then same way, p hat 2 in this case represents a sample or any sample proportion, but from population 2. And again, very similar to how I defined the dp above right here. And I want, so the rule of thumb we can recognize now is that we always go with value that's from population 1, whoever we call population 1. We want a value from population 1, subtract the value from population 2. And so at this point, feel free to pause my video and have a moment to think about the difference between these two. And the difference, I mean, how do these two differences differ from each other in terms of what they are and how we can work with them. So think about that for a little bit, and then I will get back to that. All right, so now hopefully you've had some thinking, some thoughts about this. And so now I can introduce for anyone. This dp right here simply being defined as the population proportion value from population 1, whoever population 1 is, minus population proportion from population 2 for whoever population 2 is. It could have been the other way right from the beginning, but we always want, again, we always want value from population 1 minus that value from population 2. So now I tell any viewer, I tell any of my students, this value dp, once we have defined it, it can only have this value dp can only have one unique value. But on the other hand, this dp hat right here, the difference in any sample from population 1 with a sample from population 2, this dp hat, unlike or quite opposite from dp, this dp hat, this is the truth about the value for dp hats right here. There is an unlimited number of values for dp hats. So dp can only have one unique value, but dp hat, there are many, there are a lot. So take another moment, or feel free to pause the video to think about of the reason why it's like that. dp has only one unique value, whereas dp hat here for dp hat here there is an unlimited number of values. And so now at this point, as soon as viewers and my students can agree and thoroughly agree that dp hats, which is defined as a p hat 1 value minus a p hat 2 value, has infinitely many values, then now I can push it forward and now say that even though all written in lowercase, but dp hat can be generally regarded as a random variable. So RV of mine here is short for random variable. And as a matter of fact, it is, I have to open another parentheses here, it is a continuous random variable. So that's the first fact to understand about the value of dp hat once we have defined it. So it's now we realize that it's now a continuous random variable, simply because anyone at this point has agreed that dp hat defined as following has infinitely many values. And so the next impact of understanding dp hat as a random variable now is that dp hat as a random variable, even though I'm written that all in lowercase, but dp hat here represents an entire sampling distribution, or it is dp hat itself is a sampling distribution of sampling differences between a p hat 1 and a p hat 2. So p hat 1 is just simply a sample proportion value from population 1, any sample proportion value from population 1. And p hat 2 is a sample proportion from population 2, any sample proportion from population 2. And now before we actually head out for any problem and specifically setting this problem into an actual example, then I would like to mention that the reason we allowed sample sizes n1 and n2 to be different, or the reason that it is okay for sample sizes n1 and n2 to be different, is that because the kind of problem here we are doing is being regarded as independent, or the samples that we are doing here are considered as the independent samples. Or sometimes we can also refer to this as unpaired or unmatched samples. And I won't be able to explain what exactly independent samples means or unpaired or unmatched samples mean in this video. It will wait until you see my other videos, which will come at some other time, about what it means by being dependent samples or paired or matched samples. Then I can also explain there what it means by being independent samples or unpaired or unmatched samples.